over Tristan's problems. There's two problems that covers the four checkpoints of hydrostatics, buoyancy, Bernoulli, and extended Bernoulli momentum balance. And so this first problem covers both hydrostatics and Bernoulli equation. There's an additional internal fluid flow with friction loss, but I'm not going to cover that since I already explained that portion in my video. So in this first problem, there's a waterfall that falls and drops into a tube that's connected to a manometer. So we're going to use Bernoulli to measure the velocity at the bottom of the waterfall, and then hydrostatics to measure the pressure drop across the tube below the waterfall. And so we're going to make a few assumptions. That is, the flow is steady and incompressible, and all entrance effects are negligible. So to start, we write the Bernoulli for the waterfall, and it simplifies down to the Torricelli equation, which is V2 is equal to the square root of 2gz, z being the height of the waterfall. And so we can solve for the velocity at the bottom of the waterfall to be 9.9 meters per second. And then to solve for the pressure drop across the pipe, we're going to simplify that equation down to find delta P is equal to the density of water times the change in specific gravity of mercury to water times GH, H being the height difference of the mercury within the pipe or the manometer. And so with mercury having a specific gravity of 13.6, we can plug all that in to get a pressure drop of 833,000 pascals. And so for his second problem, covering both buoyancy and macroscopic momentum balances, there's a battle between Sandman and Spider-Man. Spider-Man turns Sandman into mud, and he goes into a pipe and experiences a pressure drop. And so we're going to write out the extended macroscopic momentum balance for the Sandman mud going through the pipe to find the shear stress on his body in the sand due to the pressure drop. And so the shear force is going to be the negative pressure drop times the diameter of the pipe divided by 4 times the length of the pipe, which turns out to be about 4.5 pascals. And then finally, we're going to find the buoyancy of the Sandman when he's floating in a swimming pool. He somehow makes it to the swimming pool through the pipe, and we can know the buoyancy force is just the rho, or the density of the water, times the volume that is displaced times gravity. And so we can find a buoyancy force of 28,767 newtons.